So let's start by breaking this up into two separate equations. That's the x plus 5 is equal to negative 10, but also x plus 5 can equal positive 10. And if we subtract 5 from both of those equations, we get our two solutions. X is equal to negative 15, and also x is equal to 5. So for this one, same idea. 2x plus 7 can be equal to both negative 1 and positive 1. We'll subtract 7. We get 2x is equal to negative 8, and 2x is equal to negative 6. Dividing both sides by 2 gives us x is equal to negative 4, and also x is equal to negative 3. We have 3 minus 5x is equal to negative 12, and also positive 12. Can subtract 3. This gives us negative 5x is equal to negative 15. Also negative 5x is equal to 9. Dividing both sides by negative 5. Across the board, we have that x is equal to 3, but also x is equal to negative 9/5. All right, here we have 0.5x plus 3 is equal to both negative 2 and positive 2. Subtract 3. We get 0.5x is equal to negative 5. 0.5x is equal to negative 1. To get rid of a 0.5, you can just multiply both sides by 2. So all I'm going to do is my next step is double both sides. I get that x is equal to negative 10, and also x is equal to negative 2. So we have 4 minus 0.1x is equal to both negative 7 and positive 7. Subtracting 4 yields negative 0.1x is equal to negative 11, but it's also equal to 3. Here, to cancel the negative 0.1, I'm going to multiply both sides by negative 10. That'll cancel the negative and the 1/10. So I get x is equal to positive 110, but also negative 30. Here we have 3/2. X minus 1/2 is equal to both negative 1 and positive 1. So I'm just going to multiply both sides of each equation by 2. This gives me 3x minus 2 is equal to negative 2. Actually, that is a mistake. That should be a 1. And on my other equation, if I multiply both sides by 2, I get 3x minus 1 is equal to positive 2. So now I can just simply add 1 to both sides. I get 3x is equal to negative 1. I also get 3x is equal to 3. Here are my two solutions. I have that x is equal to negative 1/3. Also, x is equal to 1. All right, the same idea holds true with absolute value equations, where I can let the two equal each other and also one equal the negative of the other. Here are my two equations. They'll be slightly different. In the first one, I'm just going to start by distributing the negative. And so I'll solve that one separately. I guess I will add 2x to both sides. And at the same time, I'll also subtract 4. So I get 3x is equal to negative 11. If I divide both sides by 3, I get x is equal to negative 11/3. And in my other equation, going back to x plus 4 is equal to the positive of 2x plus 7, I will, I suppose, subtract x from both sides and also subtract 7. So this gives me negative 3 is equal to x. Those are my two solutions. All right, 1 minus 7x can be equal to negative 6x plus 5, but also it can equal 6x plus 5. Okay, let's solve these two equations. Start with the one on the right. We have 1 minus 7x is equal to negative 6x minus 5. I will add 7x to both sides and also add 5. That gives us 6 is equal to x as one of our solutions. In our other equation, I'm going to, I guess, add 7x to both sides again, but then this time I'd have to subtract 5. And so I get negative 4 is equal to 13x if I divide both sides by 13. I have my answer, which is negative 4/13 is equal to x. All right, I'm going to let 3x minus 1 equal negative 5 minus 2x, but also 3x minus 1 equal to 5 minus 2x. On the left equation, I'll start by distributing the negative, which gives me 3x minus 1 is equal to negative 5 plus 2x. I'm going to subtract 2x from both sides and also add 1. I get x is equal to negative 4. On my other equation, I'm going to add 2x and also add 1. I get 5x is equal to 6 after dividing both sides by 5. I get x is equal to 6/5. All right, my two equations will be 3 plus 4x is equal to negative 4x plus 1, and also just 3 plus 4x is equal to negative 4x plus 1. On the left equation, I'll distribute the negative. I get 4x minus 1, and I think I'll subtract 4x from both sides. I'm noticing that I can stop at this point because the net result is going to be 3 is equal to negative 1, and this is false. So this gives us no solution. In my other equation, if I add 4x to both sides and also subtract 3, I get that 8x is equal to negative 2, dividing both sides by 8, and reducing the fraction gives me x is equal to negative 1/4. 6x plus 7 is equal to 8 minus 6x, and also 6x plus 7 is equal to the negative of this. Solving the equation on the left, I will add 6x to both sides and subtract 7. I get that 12x is equal to 1. Dividing both sides by 12 gives me 1/12. And for the other equation, I think something's going to go wrong at this one. After I distribute the negative, I get 6x plus 7 is equal to negative 8 plus 6x. Those 6x's cancel after I subtract them from both sides. I get 7 is equal to negative 8, and that's false. There's no solution. All right, and for this one, 0.5x plus 4 is equal to negative of 2 plus x, and then 0.5x plus 4 is simply just equal to 2 plus x. Let's see what happens with this one here. On the equation on the left, we'll distribute the negative. I think I'll add x to both sides. Actually, I think I'm going to double everything. I'm just going to multiply both sides of this equation by 2 because it's going to cancel the 0.5. I get x plus 8 is equal to negative 4 minus 2x. Now what I'm going to do is add 2x to both sides and subtract 8. I get that 3x is equal to negative 12. And if I divide both sides by 3, I get x is equal to negative 4. In my other equation, again, I'm just going to double everything. I get x plus 8 is equal to 4 plus 2x. If I now simply subtract x from both sides and also subtract 4, I get that 4 is equal to x. For question 13, we can refer back to problem 2, where when we had an equal sign here, it was negative 4 and negative 3 that were our two solutions. I'm going to mark those on the graph. This is where they are equal, and that is negative 4, and this is negative 3. And as we've discussed, the answer is either between those two values, or it's on the outside of those values. Now, the absolute value is this portion of the graph, and between the two values, it's where it is less than equal to 1. So this means my answer is going to be all x's from negative 4 to negative 3. To solve question 14, we're going to use problem 1, where we got the two solutions for negative 15 and also positive 5. On my graph, that appears here and here. So it makes sense that negative 15 and positive 5 are the two solutions. Now, the place where the absolute value is greater than 10 is referring to this portion of the graph, as well as this portion of the graph. My answer to this problem is therefore all x values that are less than or equal to negative 15, or any x value that's greater than or equal to 5. I'm including an equal sign here because there's an equal sign in the original question. Just like up here, there was no equal sign, which meant I didn't want an equal sign in either portion of those. For problem 15, I'm going to refer back to problem number 3. So we know the two solutions are going to be 3 and negative 9/5, so we already solved for that. And on the graph, that must be referring to this spot and this spot. And this one certainly is at 3. This is roughly where negative 9/5 is located. So where is 3 minus 5x an absolute value less than 12 is where I'm highlighting over in green. So it's going to be between those two values. This means my answer is from negative 9/5 to 3, and including both of those values. For problem 16, we're going to refer back to problem number 7, where we already figured out the solutions are negative 11/3 and negative 3. So this would be negative 11/3, and this is negative 3. So it's either like between those two values on the outs or on the outsides of them. Now here we have to be careful about distinguishing the graphs because they're both absolute values. It turns out that the red graph is the absolute value of x plus 4. I'm confident about this because 4 is the y-intercept. You put 0 in place of this thing and you'll get 4 back. So that must mean that the blue graph is equal to the absolute value of 2x plus 7, and certainly 7 is where it's crossing over the y-axis. So this is the absolute value of 2x plus 7. So with all that in mind, where is the absolute value of x plus 4, the red graph, bigger than the blue graph? You might have to adjust your window to see it, just be careful, but it's this portion of the graph right here. I know where they're equal, and that's the only spot where the red graph is above the blue one. And what this means for us is that the answer is actually between the two values. So that's from negative 11/3 to negative 3. For problem 17, we're referring back to problem number 9, where we already found the solutions are negative 4 and 6/5. So to mark those on here, there's the one at negative 4, and this is a little bit past 1, so that's got to be 6/5 and negative 4. Okay, I want to know where 3x minus 1 in absolute value, that's got to be the red graph, is greater than or equal to the absolute value of 5 minus 2x. It's got to be the blue graph. So the place where the red graph is above the blue graph is here and also here. That's enough for me to say that it's on the outside of the two values. So my solution for this one is x is less than or equal to negative 4, or x is greater than or equal to 6/5. For 18, we're going to use problem number 10, where we got that there was only one solution that was negative 1/4. And that appears to be the case, that there is in fact only one solution. So that is nice in the fact that the answer is either going to be greater than or less than this number. So correctly labeling the graphs is going to be important. The blue graph appears to be negative 4x plus 1, whereas in absolute value, and the red graph is 3 plus 4x in absolute value. So where is 3 plus 4x in absolute value less than negative 4x plus 1 in absolute value? So where's the red graph below the blue graph? That's referring to this portion of the graph here. This means that the answer is x is less than negative 1/4. Problems 19 through 24 are referring to the functions f and g as listed above. So let's first compute f of g of x. So this is just strictly understanding the definition of composition. What this says to me is you pick x equals 0, it first goes through the function g, and then it goes through the function f. So if you first put 0 in place of the function g, you get 5. If you then take the number 5 and put that into the function f, what we get is 46. And that means the answer to this problem is 46. Question 20. All right, this is f of g of negative 2. Again, the idea is you're taking x equals negative 2, and you're putting it through the function g, and this gives you 7. You're then taking that number 7 and putting it through the function f, and you get 92. So that's the answer to this problem. For 21, g of f of 0, okay, we're kind of going backwards here. We're still starting with 0, but I'm going to first go through f. So when I do that, I get 1. I then take 1 and I put that number into g, and I get 4. So the answer here is 4. For problem 22, I want g of f of negative 2. Again, being careful, I'm going to still use negative 2 for x, but when I first go through the function f, I get 11. And then when I take 11 and place that into the function for g, I get negative 6. So that's the answer here. And notice that for 19 and 21, reversing the order in which you compose changes the answer. This one was 4 and this one was 46. Likewise for 20 and 22, I reversed the order in which I composed the functions, and we ended up with different numbers at the very end. All right, so now for 23. f of 0. So that's a little strange, but you can compose a function with itself. There's nothing that says you're not allowed to do that. You would start by taking 0 and putting that through the function f, and the answer that you get is 1. But then you take 1 and you put that thing back into the function again, and you get 2. So the answer here is 2. And likewise, you can compose g with itself. That is, what is g of negative 5? Here we're starting with negative 5 and putting that through the function g, and we get 10. You now take 10 and you put that into the function for g, and you get negative 5. So that's the answer here. Question 25, we're going to find first f composed with g of x, and then g composed with f of x, and then find their domains. We're not going to simplify these, we're simply going to write them out. F composed with g is x minus 7 squared plus x minus 7 plus 1. And that's it. And g of f of x means we take the function f and put that in place of g. So that's going to be x squared plus x plus 1 minus 7. Obviously, these could be simplified, but we're not going to. I will note that the domain for each function here is all real numbers. As we discussed in class, if the domain and range for the original functions are both all real numbers, the same must be true for the compositions. Starting with f composed with g of x. All right, so here it's going to be 50. Then we have 3x squared minus x to the fourth minus 14 times 3x squared minus x. And for g of f of x, this will be 50x to the fourth minus 14x squared minus 50x to the fourth minus 14x. And as in the previous problem, the domain is going to be all real numbers for each of these functions. For 27, let's examine the functions f and g at the start, just to look at their domains. For f, I'm just going to note that x cannot be equal to 2. Any other number can be put in place of x, no problem. And for g, the domain is all real numbers. You can put any number you want in place of x. How does this affect our compositions? Let's check it out. F composed with g of x is equal to 1 over, I'm going to put x plus 5 in place of that x and subtract 2. I'm actually going to simplify this one as well. We get x plus 3. If we get the composition g of f of x, this is equal to 1 over x minus 2 plus 5. Now for the domains, it's really obvious, I think, for g of f of x that you can't use 2. It appears right in the formula. So I'll say, this is my domain, every x value except 2. I can see that a 2 can't go here, but also, you would first have to put 2 into the function f, which we already decided you're not allowed to do. It is a different situation for the function f of g of x. Now it's negative 3 that causes a problem. The domain of f of g of x is x cannot be equal to negative 3. The reason is, if you put negative 3 in place of x, it first goes to g, a negative 3 here sends it to 2, but you can't use 2 in this function. Again, at the start here, I'm going to note that, okay, the domain for f is every number except negative 1, but g, everything's okay. You can use all real numbers, no problem. So if we're looking at f composed with g of x, that is 3 divided by x squared minus 5 plus 1, or simply 3 divided by x squared minus 4. For g of f of x, that is 3 over x plus 1 squared minus 5. I won't simplify this one. Same situation as last time. I can easily see that for g of f of x equals negative 1 is no good, but everything else is okay. That number would first have to go through f, but it can't. Something odd happens, though, in f of g of x. There are 2 numbers that you're not allowed to put in place of x. It's any number that would make x squared equal to 4. If this whole thing was 4, 4 minus 4 would be 0. And x squared is equal to 4 for precisely 2 values. X is equal to 2. Think about it, if you put 2 here and square it, you get 4, and 4 minus 4 is 0. But you can't use negative 2 either. Every other number is okay. Problem 29, we talked about this in class. The domain of f is all real numbers. The domain for g is all positive numbers. You can't have a negative number under the square root. When you look at f composed with g of x, it might be nice to even leave this as the square root of x squared. Now you can simplify this as x, but it turns out that the domain is going to be all positive numbers and 0. Even though this is x, and x just all by itself is defined for all real numbers, you're not allowed to put negative numbers into g, so we still need this restriction. Whereas, if we look at g of f of x, this is going to be the square root of x squared. Here, all real numbers is the domain. You can put any number you want in place of x and square it, and by squaring it, you'll never get anything negative under the square root, so it's perfect. But as we saw already, this is not equal to x. In fact, it's equal to the absolute value of x. So this is kind of important. If you take the square root of x squared, it's actually equal to the absolute value of x. So just an identity that I'll state down here. Question 30 is basically what we did earlier where we're evaluating a composition, but here we're doing it from a table instead of formulas. So if I want to figure out f of g of 1, first I'd have to know what g of 1 is equal to. So I find 1 in my table and I put it into the function g and I get 5. That number 5 goes into the function f and the answer here is 2. So again, the reason was this 1 starts in the table for g and it gives you 5 back. It's then this number 5 that goes into the function for f to take you to 2. Here, let's try this with the remaining ones. F of g of 2. What's that? Okay, so I first have to put 2 into this table for g. It gives me 0. I then take 0, put it into the function for f, and my answer is 4. G of f of negative 1 means I'm now starting in the table for f at negative 1. So this negative 1 says start here, and you get negative 1 back. You then put that negative 1 into the function for g, and you get 9. And lastly, what is f of 3? So we go to the table for f and locate 3, and we get 0. But now it's like we go back, but we're going back to the same table to 0, and that takes us to 4.